In this video, I'm going to talk about decoding. So in the last video, we talked a bit about hidden Markov models and how we could represent our hidden Markov model as vectors and arrays and matrices. So we also try to compute the probability of an explanation giving some observations. Well, a probability of the pair. So in this video, we're going to be talking about decoding. So this is a particular problem you might want to solve given your hidden Markov model. So the problem is, given observations X, find the most likely explanation Z. So to be a bit more formal, I'll just actually call this Z star. To be a bit more formal, what I really want is I want Z star to be the argument that maximizes over Z the probability of X and Z given theta. So theta, if we just go a bit back, it's our model. And, well, then basically I just want the Z that maximizes the probability. So before we could kind of compute this, we saw how to compute this probability of, so I might just note that capital X is x1, xn, and the capital Z in this notation will be z1, zn. So then this guy is basically the probability of x1 through xn, z1, z, and these shall be capital N's. Sorry. So we know how to compute this probability under our model. Now I just want to find the C that gives me the maximum probability. So what I could actually do here is I could try all combinations of Z, and I could just compute all of them and take the one that's the most likely one. So let's just consider how many possible Z's are there. So if we look at the example we had over here, in each position I could choose, so this would be Z1, Z2, Z3, Z4, Z5, Z6, and Z7. So in each of them, I could choose high pressure or low pressure. So I have two choices for each guy. This would give me 2, 4, 8, 16, 32, 64, 128 possibilities. 2 to the 7th. So in the general case, this will give me a K, because each of the hidden states can be in K states, to the N, capital N possibilities. So if I just wanted to compute this blindly, this would be the time it would take. So it turns out that there's actually a very efficient algorithm for this. So there's an algorithm and it runs in K squared, it's K squared in time. So this is exponentially more efficient here, and you could, so a realistic case could be maybe have 10 hidden states, and n is like DNA, so this would be like 10 to the 9th or something like that. I mean, you could get really large stuff here, right? So this would be very large, and this guy over here, like, this would never happen, right? This is not something you'd be able to compute on the computer, and this is something that might be doable, right? If you have a lot of computing power. So maybe not 10 to the 9th, but you could have something large up here. So let's try to look at how we arrive at this algorithm. And so let's try to rewrite this thing. So maybe if we look at the probability of X and Z given theta, or maybe let's just not write theta and have it implicitly now. So then this probability will be P of, let's look at the probability of X and the optimal Z star. So this will be the same as maximizing over Z, probability of X, Z. So now let's try to insert this. So let's try inserting that we have these capital N guys. Then this will be the max of z1, zn, and px1, xn, c1, cn. And this will in turn be the same as, well, the order of the maximization doesn't really matter, so we could change the order and maximize over the capital N as the first guy, and then maximize over the other guys. So this is 1 through Zn minus 1. Capital N, C1, Z capital N. Great. So what we do now is we take this guy and actually we define something we call find omega to Zn, and we want this to be the max over Z1 to Zn minus 1, and then the probability of x1, xn, and z1, z capital c little n. So notice this is, I used little n here to index, and then the other n's are capital N's. So this, you might usually be familiar with people using a little I for indexes instead, but to be consistent with the lecture notes, I'm going to use a little n here instead. So this is why it's important I use capital N's up here. But so if we define this like this, then omega to z capital N, omega c capital N would be max of z1 to z capital N minus 1, probability of x1 through x capital N, z1, z capital N. But this is exactly what we have over here. So then this would be max over z capital N omega of z capital N. So now we kind of just renamed stuff. We didn't really do anything interesting here. But it turns out that this guy, and this is, let me just write it as a theorem. A theorem. So omega, so it turns out you can compute this guy efficiently. So omega of z1 is the probability of x1 and z1, which using conditional probabilities you can write this as c1 p of x1 given z1. But then and this is the recursion step, which is kind of the interesting thing, is that you can compute z little n as the probability of xn given zn, and then a maximization over zn minus 1, and then omega z n minus 1, and then probability of zn given zn minus 1. So I'll for now just let the proof of this be in the lecture notes. If I get time, I'll make a video later where I go through this proof. It's actually not that complicated. You just need to know 2 tricks in rewriting this omega guy. So you're looking at this, and then you're using the fact that you are using hidden Markov models. That's one of the guys. And then the other one is just you have this product, and then you're just counting the product down and then moving around until you get the same thing. Anyway, what we need to do now is we need to consider how do we actually compute this. So in the previous note, we considered that we could represent our hidden Markov models with these vectors and matrices. So let's say we have those guys. Then how could I kind of compute this table or this omega thing? So what we do is we have a table of size of k times n. So maybe let's actually just do an example. So let's continue the example we had over here, where we had the possible hidden states was high pressure, low pressure. So then instead of then K would be 2. So I'd have like high pressure and maybe low pressure, and then I would have like 7 observations. So I'd have rain, then 3 times sunshine, 3 times rain, sunshine, and then 2 rain. So this would be sorry. So I'll be something like this. So I'll have like sunshine, I'll have rain, 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 sunshine, rain, rain. So this will look like this. So then the first column here I would fill using the base case. So this is kind of the base case, and this is the recursion. So then I could say, well, this is the probability of starting in H. What is the probability of this? Wait, sorry. What is the probability of starting in Z1? So you could look at the probabilities in here. Well, oh, so actually I didn't write these down. Yeah, so let me just try to just give a little bit of a bigger picture here. So in this case over here, I said you were given hidden states. So what we're doing now is actually we are only given the observations, and we want to find the most probable one. We want to find the most likely one. So we're not actually given these guys, but we are given the x's. So now we want to find what are the most likely combination of these, given our hidden Markov and giving H and L, giving these observations. Great. So given initial probabilities, then you'd be able to compute these values following this formula. And then let's say I wanted to compute this guy. Then what I'd do is I would say, well, what is the probability of being in low pressure? So I'm in the low pressure state, so I would have like so the first guy here would be probability of low pressure, and then emitting rain, right? This is my observation. So this would be the first guy, and then I would take a max over the possible values of the previous state. So then this would be the max of high pressure or low pressure. So I could maybe write it as like a max, and then I'll have like high pressure here, and I'll have low pressure over here. So then I will look at the value just before. So this would be like the value here for high pressure. So let me just write this. Let's call it omega h. So omega sub h, just for the value that's already in here. So we'll fill this matrix like here, and then we'll fill here. So I'm just saying, if I wanted to fill this, what would I do? So I'll already have computed this area by then. So then it will be this value, and then times the probability of transitioning from the high pressure to low pressure. So like be the probability of being in low pressure given the last state was in high pressure. So this is like the transition probabilities of high pressure to low pressure, right? So that will be what we'll write here. And then in the other guy, I will take the omega value of this guy, and then the probability of going from low pressure to low pressure. So this will be whatever value is in here, and then times the probability of going from low pressure to low pressure. So I'll just try to maybe make this as a bit more general. So in the bit more general case, you'll have like a table like this, and you'll maybe look at so this will be like k guys, and this will be n, and then if you want to compute the ijth entry, you'll look at the column just before, and you'll be like, well, what is the probability of emitting whatever observation I saw? So the probability of emitting whatever observation given I'm in state I, and then you'll be like, oh, what was the value the first guy in the column before me, and the probability of transitioning from 1 to I, and then you'll be like, well, what is the value in the second guy and transitioning to this guy, the third. You'll do this all the way down, so you'll have all of these guys, and then you'll take the maximum of all of these guys, and that will be the value. So just to kind of see how we get to this time complexity, well, in this cell, I'll have to look at k guys, okay? So this will kind of be like order n operation, because I have to do like constant work k times. But so how many times do I have to do k operations? Well, I have to do that for each cell of the entire table, and the table is size n times k. So then this becomes that times n times k, but this is the same as k squared n. So this is the time complexity. Great. So let's try to look at the code and see if we have anything in here that's oh, I see. Sorry. This is my recording software. I'll just make that go away. Great. So this is Python code that computes what we just discussed. So let's see if I can. Oh, maybe full screen this. Great. So my model will contain the parameterization of my hidden Markov model. So I'll have like pi, a, and phi. These will be named initial probabilities. There will be phi. Emission probability. Initial probabilities will be pi. Emission probabilities will be phi, and transition probabilities will be a. So I'll get the model which encodes these guys, and I'll get my observations. And now I want to find the most likely z. So I'll just denote k and n by the sizes of these different things. In what I just did, this was like capital N, but let's just keep it at little n. Then I'll initialize my omega table, but I'll just call it W for sake of ease. And this will be an array storing the final, the most probable. Well, actually, yeah, I really don't know this. I'll need this later for backtracking. Sorry. So this will be what I'll need. So now what I'll do is I'll try to compute the first row. So let's just get back in here. And so what I do here is I look at the first column of omega and I loop for each hidden state. So in this case, k would be 2, so I'm looping for these two guys. And then I'll be like, well, what is the initial probability of starting in state 0? Well, that's a probability of initially starting in high pressure. And then I'll multiply this with the probability of emitting the first symbol observation. In this case, that would be sunshine, given I'm in state 0, which would be high pressure. And that'll be the value I'll store in this guy. And then the next round, j will be 1, and I'm 0 indexing here, so this will be 0, this will be 1. So then this would be the probability of starting in low pressure multiplied with the probability of emitting sunshine given I'm in low pressure. So now I'll fill the first column, and then I'll get to the recursion step where I can now I'll loop over the column. So I'll take j as 1, and then I'll loop over all these guys. So now we could maybe just say, well, I successfully filled up these steps, and let's say I look at this guy. Then I'll say, oh, so j is 0, 1, 2, 3, and I will be 0. And so again, I'll just do exactly what we did before. I'll say, well, the emission probability now will be the probability of emitting the jth observation, which in this case is rain, given I'm in the hidden state, well, 0. Then comes the maximizing part, and this is probably a little bit more tricky part. So what I do here is I use list comprehensions in Python. So I just loop over all values of k. In this case, it's only going to be 2. So I'm going to look at what is the transition probability of 0 to the state I'm in right now, and 1 to the state. So this corresponds to the transition probabilities. These are the guys we had here. And then this will just be looking at the previous states. So this is kind of annoying. So the transition probabilities will be from going from the high pressure to low pressure and low pressure to low pressure, and then the value here will be what I called omega h and omega sub L. Great. So this is a bit more general, right? This would also work in the case over here. So this is the code for doing it. If you're taking the AU machine learning course, you would also be able to run the code, and you should get something like this. And sure not, this might not make any sense. I mean, these are just arbitrary values. Great. So I think this is all for this video, and then the next video I'll talk a bit about backtracking. So now we computed the value for the most probable explanation. So given observations, we found the most likely explanation, find the one which maximizes the probability, and in the next one we're going to try to recover the z, which is actually what we want to do. Right now we just computed the probability and we actually want to find the z. Great. So that's what I'm going to discuss in the next video. And also, there's going to be some rounding probabilities here with some floating point issues. I'm also briefly going to comment that in the next video.